So log into the community edition. And those who were maybe not here yesterday should hopefully have the community edition. Now, so I'm going to simply go and right-click this importable Databricks notebook, copy link address, and come here and just throw it here. Oh, by the way, it's important, so let's get this out of the way. So go to your workspace and create a folder. Okay. I want you to create a folder named Scalable Data Science. Okay, so like this, we will need this root. Okay. So from the workspace, you should have this folder. I won't hit create folder because I already have one right here. Okay, and later on, we will throw in another DBC archive in here for visual aid of the ideas later. Okay, so now let's just go back to home and so I'm going to import and from URL, and I'm going to paste that thing I just copied, right? This is the Scala crash course. So it just renames it as one because I already have another notebook by the same name. Okay, so this is what we were doing yesterday. And what you need to do is create a cluster. So I just created one, so it keeps running for up to 1 hour if it doesn't get any sort of input from you, and then it automatically shuts down after an hour. So everyone should be at the point where they have this notebook and they have attached it to a cluster that they started. Is anyone not here? Okay, good. So, so this was just some basics of how to play around. And we got to sort of the bottom here, you know, printed milliseconds and why Scala. It's an interesting mix of object-oriented and functional. It does static type checking, immutable and mutable instantiations of variables, assignments, you know, some kind of type inference for compile time, so you don't have to be too explicit. Then we did this. This thing worked today for me, S dot. I was on Ethernet cable, and I was able to go to Oregon and come back with the methods pop up. So it wasn't, I don't know, maybe we're just too many people going from Sweden. It could be a traffic problem here. So and then, you know, just you do methods and so on. And then we started defining functions. So, you know, so you have to be explicit about the types. Generally, I am. And I think you can kind of go generic, but it's a little dangerous. You need to really know Scala properly. You can return units and some things, and some is the generic thing. I don't want to go there. Okay, I'm not an expert in Scala. So let's sort of quickly get to closures. So these are just functions, and then Scala collections, just lists and arrays and sequences and so on. And this is essentially closure. So they're also called anonymous functions, and they're kind of the primitives for functional programming. So in Scala, functions are first-class citizens. Right? So here are 5 ways of adding one. I can just do int. I can just do this, x colon int. So x is of type int, and I want to add 1 to that x. And I put this equal and great, that's fine. So I can also say x maps to x plus 1. Right? And I can also use placeholder syntax. I can say whatever underscore +1. Because remember, this is going to be part of something else, usually a map. So here's a more explicit one. This is a type inferred, more intuitive version of code block. So if I, sorry, just trying to make it slightly bigger in case someone from India is watching from a tea stall under low resolution, you know, it'll be good for them too. So Control F, and then closure. There's 4 instances of this. Okay, so this is very useful because now you have a body, you have a curly brace, and then you can say all kinds of things in here. You can actually instantiate vals and bars and whatever. So as long as they're native types like strings and ints and so on, and done in Scala, then the beauty is everything in this closure is shippable. Shippable to me simply means you know, when an object is in the random access memory in the von Neumann architecture, which is all we have, except quantum computing, but I don't know, we don't have access to those. So then, you know, the objects are in RAM in a certain state, and then when they go from RAM of one machine to the RAM of another machine, they have to go through Ethernet cables. So you have this process of serialization and deserialization. And so these whatever data structures, things in memory, zeros and ones, they need to be able to you know, have methods for serialization and deserialization as they go through Ethernet cables. Okay, it's a very high level, but the nice thing is a lot of the native types are already have these things, and there's also, you know, cryo serialization and efficient compression and things like this. So because there's an order of magnitude, a couple orders of magnitude difference in the rate at which data can pass through Ethernet cables versus, you know, memory, we need to try to minimize that, and that's in fact the whole art of Spark programming. Okay, so this is a simple example. Here it's just you know, regular function. So now let's apply closures for functional programming. So we can say, so you have to create a list first. So I'm not sure if list exists, so let's check. Yeah, so there's a list, there's an integer of 1, 2, 3. So let's try this. So I'm just saying for each is a method. It simply applies whatever is in the closure, which is printing x to every element of the list. So that's a nice iterative one-by-one map, right? You can also do list.forEach. Do list.map. So now I'm going to map every element x to x plus 10. So I try to write like this without using underscore magic because it gets crazy when. So Scala, a lot of criticism is that you can kind of have your own tribe of whatever tribe dialect in. It can get too weird. So I try to keep it a bit. But when it's obvious, I use underscores, right? Because it saves a lot of typing. So this is another way. Underscore plus 10 is exactly the same as x maps to x plus 10. And now I can filter. So this is another thing. So in the closure, I need a Boolean expression. And so everything that satisfies this expression is filtered. So here I'm essentially trying to do percent is modular operation. So I'm basically throwing away the even numbers. Okay. Sorry, keeping the odd numbers. It's a difference, right? Okay, so just whatever the remainder is one I keep. And then the same as above, using placeholder syntax. So we can just do the same. Now this is very useful, and we will do this in word count already. So now we have a tuple of size 2, an ordered pair, x comma y. This is parentheses around it. So now I'm reducing it. So reduce operators basically take a sequence, and then they apply things to 2 at a time. And usually 2 things become 1 thing, and then that one thing gets done two at a time with the next thing, and so on. Right? That's basically reduce. So map and reduce. So Google introduced MapReduce, I guess, in 2004-ish. Anyway, after the Preagle yesterday, we talked about the Preagle model for distributed bulk synchronous parallel programming on like programming vertices. So that's something before MapReduce that Google open sourced, and then MapReduce was the one. And of course, Yahoo had this whole Hadoop ecosystem that was built on MapReduce, right? So if you watch the videos, you should try to put what I'm blabbering together with the few Watch Now videos from yesterday. So the main idea there is that the data is way too much, so it cannot be in one machine's hard drive. So you need hard drives of lots of machines. Just because you have terabytes of hard drive doesn't mean you can read from all of it fast. So you need, even if you have terabytes of one hard drive, you need to actually have multiple machines reading chunks of it, basically. So it's better to have lots of smaller hard drives. So that way one machine fails, you still have to somehow find the missing, the lost data from somewhere else. So that's usually done through these Hadoop file system, which is essentially an open source version of Google's, to implement Google's MapReduce, mainly by Yahoo and the community, right? So that's Apache project as well. So there, it's a lot of details, but essentially you have name nodes and things like that. At the high level of abstraction, you can simply say, I have all my files. I basically have redundant copies of the files and some metadata that tells you where the redundant copies are on different machines. So as long as a fraction of machines are still functioning, you can determine that fraction. And I think for number theoretic reasons, you cannot have more than 1/3 random machines breaking at a given time. This is some very deep maths behind it, right? Because remember, why number theory is important here is because all the protocols on distributed computing can be implemented directly from the most elementary protocol, which says, which is the synchrony protocol. It says, I'm at step 1, and the other machine says, I'm at step 1. They need to agree on what step they are. As long as all the machines agree on what step they are, you can implement every other protocol on top of this protocol. And to do this, you need some elementary number theory, especially when some of the machines are going down, right? So I'm not an expert on this. I just was at a seminar. Okay, so there are other reasons, but mostly because we have guarantees or manufacturing warranties on disk failures and things like this, we can safely assume, not 1/3 of the machines will go down. And in the industry, I think Netflix has this thing called the Chaos Monkey. Has anyone heard of Chaos Monkey? So Chaos Monkey is a really interesting program that goes at random and turns off machines, simulating machine breakdown. Right? So of course the game is, can you stream movies to wherever in the world when the Chaos Monkeys turn loose? And of course the Chaos Monkey cannot do more than 1/3, I think. Otherwise, all the other problems, mathematical problems. All right, so let's go and do this so we can reduce, and we can get 6 because I'm just adding everything. So when you use a reduce operator, there's fold left and fold right, so the order in which you do the reduce can be controlled, and things get interesting in algebraic. But for addition, it doesn't matter which way you add. Okay, so I think it does fold. It does one of the folds by default, I think. So it doesn't matter. It's because addition is commutative. But if you had like a list of elements in a sequential container where the operation has to be associative, right, or non-commutative, there's, you have to be aware of things. Okay, so for most of the operations here, it won't matter. So this is the other one. Now let's combine map and reduce. And so we're going to map x to x plus 10 and reduce it, right? So this should be same as 1 plus 10 plus 2 plus 10 plus 3 plus 10, which is 36. Okay. So of course, I like this because I literally forget languages I wrote like thousands and thousands of lines of code on because I go to some other language. Like I'm really rusty on C++, although I was writing in C++ for 2 straight months last year in Stockholm math department. But that's life. So I document a lot, and I keep reading documents again and again. This is maybe one of the sites I visit a lot for Scala, right? So let's quickly review. Variables are var x equals 5, val x equals 5 is immutable, and it says you shouldn't do this, and good and bad for various reasons. Functions. Let's see. So we went through maps. Oh, reduce left is what I meant. So you can reduce from the left and the right, and yeah. So this gets pretty hairy now, right? 2 times, and I strongly recommend just writing a bit more explicitly, because remember, one of the main things in the data science process, by the way, we should slightly, let's come back here, but let me quickly tell you something rather important if you haven't read this yet. So I believe we had maybe here. So especially if you're sort of coming from academia, and especially after your PhD, and you want to enter industry, I think this is a very good read. Totally worth your time later. Yeah, some perspectives from current affairs. Yeah, it's a highly recommended. Let me open link in a new tab. So this is a Medium, back channel thing. It's very good. It talks about how to succeed in the industry, and what it's actually a function of your mindset. So this is really, really good. I strongly recommend reading it. One of the main things here is that you should write code so that if aliens abduct you instantly, your company doesn't fall over, right? Because there's a lot of people trying to make money off this product or whatever. So you need to write in a way that others can understand, and it's very, very important. So anyway, that's just a quick detour. Let's come back to Scala. See what else did we miss. Yeah, there are more. Yeah, so here's anonymous functions. Some other. Yeah, nothing to find. And then we will see how to use packages very quickly. So this is the syntax for importing packages. So this is importing everything basically, and very specific ones and so on. Okay, so data structures, we have tuples. So you could have tuples of various lengths. I think different versions of Scala at least had a limitation on the length of a tuple, some number. Not sure about 211 yet. So you can have lists, control constructs. So if some Boolean condition, be happy, else be sad. Okay, so that's your basic conditionals. While, there's a while loop, while something is true, do this, or do this while something is true. Yeah, so let's not get too carried away. You already seen filters. We will see flat maps. So flat maps are important because they now can take one element, and instead of outputting one element, they can output more than one element. So so it's a sort of one-to-many at the atomic level. Let's see. So we'll come to some of this later. Classes, of course, there are classes. It's object-oriented as well, but most of the time we've only used case classes. They're quite simple, and okay, that's good. That guy there. Okay, and we saw how to go to different languages. And here's an example of running Python %pi. So this should work. And so you're just printing it in Python, so the Python interpreter is running in the background. And this is R. Okay, so. And how do you babble the distributed objects between languages? So we'll come to that later. The sort of simple way is to So later on, we will see we'll have these more abstract things called data frames. And those data frames can be saved in the distributed file system in efficient formats. Parquet, for example, which is another Google open source format with efficient column compressions. So then that's a naive way. You can just dump the thing in distributed memory once you've cleaned it, and then you can just switch languages and go to Python and start sucking that in, the Parquet file, and just play it in Python, especially the guys into deep learning who want to use TensorFlow. Probably should do that, maybe. But I think this Spark 2.1 onwards, I have to learn this myself. The Spark session allows sharing in some sense between languages, but I'll figure that out before we need it or get to. But this is how 1.3, for example, we were able to babble between languages. So we'll do more of this. This is how you will do shell, %sh, right? And hash is a comment in the shell. And and man is a command that's very important. It's short for manual pages, or so if you don't know something in shell, you can man it, right? Just man bash tells me. Okay, so file systems. So %fs are the Databricks file systems, which are essentially some kind of a unified interface to various other distributed file systems under the hood. Often it's Amazon's S3, but if you're doing this type of stuff in-house, you would have your own Hadoop file system, which would be a distributed file system on your local cluster. Okay, so here's some other references. Oh, this is another nice trick to know. %run is a Databricks thing, so you can run one notebook inside another notebook. So if you have a full notebook somewhere, very well defined, then you can do %run and run that notebook from another notebook. So you can write modular, notebook-based code if you like.
Those notebooks, they should be supposed to be located somewhere in the same.
Yeah, they have to be in the workspace. So it'll be like we have some examples later on. You'll see. Yeah, so one of the products Databricks has is like people that are data scientists who want to work very closely with data engineers. Then they have these, type in the professional version, you can convert a notebook into actual production-ready execution code, things like this. Yeah, so that's Scala crash course basically. So let's now try to do the next thing, RDDs. Okay, so let's play the same game. Copy link address, and I'm just going to import the URL. Yeah, I left India in 1991, right? So India has fiber optic cables over the entire country. It had fiber optic cables before New Zealand. So I should maybe make it small, right? That was their development strategy, right? Gray matter farming, feed the humans and some light speed communication. All right, so here is essentially today's notebook. So what are we going to do? RDDs, I'm going to get an idea. I'm going to play a few videos so that I know for sure you guys are on the same page. And then we will study lazy transformations and actions. And we will create RDDs and then perform these transformations and actions on them. So what I want you to recollect now from the 001 Y Spark notebook and AJ's videos. First of all, did you watch it? The ones that said watch now? Okay. Okay, so that's good to know. So I'll be writing all the code for you, telling the driver what to tell the executors to do, right? So the driver does the following. It connects to a cluster manager. So this is the cluster manager. And the cluster manager allocates resources across applications. And it acquires executors on the cluster nodes. So the cluster nodes are your machines. And executor processes run compute tasks and cache data in the memory or on the disk if it can't fit in memory on a worker node. Right? So we have a driver that essentially connects to a cluster manager that allocates and manages resources across various applications. So the word count we'll be doing is like a little Spark application. The driver acquires the executors who do the work, or slaves, and these executor processes are going to run various compute tasks, and these tasks will cache data in the random access memory of each node, and then depending on what is the task, we have to be careful about how the data gets shuffled and things like this. Then it sends the application to the executor and sends tasks for execution for executors to run, right? So we will see examples of what exactly a task is and how a particular job gets broken down into tasks and things like this down the road. Okay. So this is the high-level picture. So for us to deal with fault to make sure our programs are fault tolerant, so they basically keep running even if some machines fail, we have this abstraction of the resilient distributed data set. That's the main idea of Apache Spark. So it's a fault-tolerant collection of elements that can be operated on in parallel. Right? So you can watch this later. So the two types of operations are possible on RDD. One is called transformations, the other is called actions. Right? So what the video says. So he's just showing you an example of how to work with an RDD. An RDD essentially takes a list of elements, and using this Spark context.parallelize method, you create a distributed collection called an RDD, and then you can sort of do maps on this collection. You can do maps and filters and reduce by key and whatever you want, and you can get your result. And the intermediate RDDs have different types and so on, and basically that's what the idea is. And in this 1 minute something, you can understand what transformations are. Transformations are essentially things that you do to the RDD in a lazy way. Okay, so you don't actually take the action and make it do things. So it just remembers what the instructions were in your instructions to your driver, right? And in fact, just keeps a recipe of how to create the whole process. And that's the idea behind resilience, right? So you keep the recipe of what to do so that when something fails, you can actually take the recipe and reconstruct the parts that should be in the recipe by making sure that the distributed file system finds the right things. So it's kind of abstracted in this way. So if you read the Spark paper, which is linked in that Why Spark notebook, it's probably the only white paper you should read to understand it. It's Matej Zaria's, there's a whole team in Berkeley, it's their main idea. If they talk about lineage graphs and things like this, so you have this lineage graph that keeps track of what transformations are being done to the input RDD. And remember, the input RDD always comes from your distributed file store. This is a so-called Lambda architecture, right? So you always dump all your stuff into a distributed file store that's fault tolerant, and then you do some machine learning or whatever you want from it, so that when your source data, the drive that holds parts of the source data go down, the resilience in that file store will replace it, right? So all you need to know is what is the recipe to create the downstream structures for machine learning or whatever, right? And RDDs essentially take care of that for you.
Okay. Is it necessary to have a distributed file system?
Well, is it necessary? Well, this I think is what is the Lambda architecture. So everything comes in, you dump it in some place that's robust, because the problem is there's too much coming in, so you can't put it in one disk and blah, 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 right? So you do need a way of, I mean, I'm not like a NoSQL guru or anything, right? But you have to put it somewhere. Right?
Yeah. So Spark it supports also standalone mode where you can run basically on your laptop and you can and there are different cluster managers and HDFS or some other types of distributed file systems. They're just pluggable elements.
Yeah.
And then just wondering what will happen with the tolerance, job fail tolerance, if you use just plain Linux file system.
Well, okay. Well, the fundamental problem is the data that you want to analyze is in the order of terabytes. So we cannot, you agree, we cannot put it into one machine. I think there are 3 cluster managers, at least I recall, the standalone and the Mesos one. And then the Yarn is what we're running, and I think the Zookeeper. I mean, let's not go into, I don't know enough about engineering detail. There's something called a Zookeeper that makes sure that the master can recover if the master fails. This is not my domain of expertise. But what you need to do is maybe watch these videos to get a quick cut down. Ideally, read the white paper by Mate. If not, just remember that RDDs are essentially, recalled as recipes through these lineage graphs, so that when something fails, you can reconstruct the part that fails. Okay, because you are abstracting away the fact that the distributed file store from which you're sucking all the stuff is going to take care of physical fault tolerance. So now you have to only worry about sort of fault tolerance as you are doing downstream computations, right? And RDDs take care of that for you, but the software layer. That's what these videos are actually talking about. I'm sorry, I don't know what's going on with my machine. I can't play them. Okay, so now here are the key points. Resilient distributed data sets are the primary abstraction in Spark. RDDs are immutable once created, right? So you can only transform one RDD to another. You cannot change an RDD once you've created it. Right? So you have RDD, one RDD, another RDD, that's a transformation of that, and so on. So you can perform actions on it, but cannot change an RDD once you construct it. So an action could be just reduce. Use an RDD of lots of integers, then do a reduce on it. So the action will be add, and it'll give you the sum of say 1 million elements or tens of millions of elements.
Which will be another RDD, right?
It depends. So actions actions generally will output something that will come back to the master, the driver process. So there are lots of examples. For instance, down the road, if I have a RDD that is a collection of 800 billion integers, I can create that, right? Just a loop. And then if I do .collect, all that thing is going to scream back at the driver. It'll crash the driver's Java virtual machine or whatever the memory, right? So you have to be careful what you're doing a little bit. And generally, I would like to start with RDDs because they're the primitives instead of giving you guys the abstract data frame and things like this, because this is not a course in data analysis alone. Okay, so what else? So we can construct RDDs by parallelizing the Scala collections, transforming an existing RDD. And it can be from distributed file systems such as HDFS, like usually your in-house thing, or S3 from a service provider like Amazon and so on. Google has its own as well. Okay, we can also specify the number of partitions of an RDD. So this is a fundamental construct. So the data in the RDD is partitioned. It is in different partitions. And then there are methods that will allow you to do certain transformations in a partition-specific way. So the 2 types of operations are transformations and actions. Transformations are lazily evaluated. Examples are map, flat map, filter, distinct, and so on. And actions could be count, which just counts the number of elements. Reduce is some kind of addition type thing. Or you can take some elements and just bring only, say, take 10, well, just 10 elements to the driver. Or you can collect, which is the whole shebang. Should be careful. We can do take order, So Spark transformations enable us to create new RDDs from an existing RDD, lazily evaluate, and so the lineage graph is simply the recipe for creating a result, and it can be optimized before execution. So I will say I want to do this, blah, blah. I have very complex SQL operation I want to do on all this data. And then I finally do this action. Spark, we will see later on, will actually create the logical plan, and then it'll optimize the logical plan to maybe change the order of operations, right? Maybe some things called predicate pushdown, whatever. There's lots of things it'll do automatically for you, and then find the physical plan and implement it, right? So these are abstracted away and taken care of for you, and we will come back to these ideas in a couple weeks. Something called a catalyst optimizer that does this for Spark SQL. Okay, so the other important thing is you can persist or cache RDDs. So you can just use this .cache command, and now the RDD will get absorbed into the random access memory of lots of machines. Okay, that's the big thing about Spark and why it's a big hit these last few years. Because if you sort of track this history, the last 15 years or so, what Spark did is improve Hadoop by allowing these huge data, huge data sets to be also in random access memory in a distributed way. Because in the standard Hadoop way, you wrote the file, you took it from disk, you did something, wrote it back to disk, and it took, so you have to do this incredible I/O intensive operations. That's in the second video upstairs, okay? And Spark basically said, okay, we can do that too, but why not? Because memory is getting cheap, so why not put the stuff in RAM, like make sure it's distributed RAM. And of course, machine learning algorithms are very efficient now, because what do you do in machine learning? You essentially are doing some kind of fixed point iteration in some space, like optimization, whatever, which means you need to keep the objects in distributed random access memory so that you can do operations on them very efficiently, right? You don't have to write to disk, read back again, you just play along. That's kind of the main attraction for Spark. Okay. So let's do this, and this is a do now. This is necessary. There's no videos. So I want you already created the directory called Scalable Data Science. So now copy this link, copy link address, and go to your workspace and this directory, and then import URL. Okay. So this should create a directory called extra resources here. Okay. So so I kind of started doing things here. Yeah. So we will need this path to exist. Okay. So now let's go back to. So this guy, Jeff, and Adam Brindle and whatever, these guys, they made some really beautiful visualizations. So I kind of flipped all this with some wgets and trying to make a visual set of notes. So that's what we'll do next. Okay. So at a high level, this is our game. We're going to write driver programs. This whole class is about writing driver programs. Okay. So the next set of tasks, what we're going to do is create our own RDD using this SC. SC is the Spark context, which is your fundamental sort of link into the programs. And SC is already created for you in Databricks. But if you write your own Scala code, like SPT, then you have to actually import and create the Spark context. Okay, you can say val SC equals some blah, blah, blah. And then everything else we're doing here basically can be stuck into code, okay, into proper software engineering stuff. Though we may do that later. Okay, and then what are we going to do? We're going to do get the number of partitions, which is an important function to know how many partitions there are in your RDB. We're going to perform some action like take, and a transformation map, another one filter. We will do the reduce action. We'll do the flat map transformation for the RDD. And then we will start playing with a special kind of RDD called a pair RDD. It's a key value pair, so ordered pair. And then we will do some transformations on pair RDDs. And finally, we will, try to think about where is this running. Maybe we'll get into Spark's UI to kind of have an idea of what's going on with these things you've created. Okay. So this is how you would do. So Spark context is already there for you. So, I'm just Control Enter, attach and run. Okay, so what is the output? It says it's a org Apache Spark RDD of type int. And this is a parallel collection RDD. It's the type of the RDD. So I hope this works now. Yeah. So I can now say what are the methods available for this immutable RDD I've created. And there's lots of methods. Aggregate as instance of, collect, compute, blah, blah, blah. It's quite a lot. Okay, of course, we don't have time to do all this. You can always go to the docs, the latest docs in Apache Spark to find more information. So the collect action on the RDD is what we'll do next in finding the number of partitions. So here's the sort of picture. Okay, so we have an RDD. It's sort of partitioned. So there's A and B, so two partitions, and then when we do the collect action, it's going to just give us back what we created. Okay. So here's Scala code and Python code. This is in PySpark, but we'll just focus on Scala. So if I do x.collect, I should just get back now an array because that RDD has been collected. It's now in the driver, and in the driver, it's just turned into an array, right? And I said collect should be carefully used because if you just make something really big, like even in this example, if you just do array in 1 to 10 million, then maybe more than 10 million, you might crash your driver. Okay, so get num partitions is sort of a first peek into how is this RDD structure, like how many partitions are there. So in this case, it'll in this picture there are 2 partitions. And then you can get the number of partitions, and it's 2. So glom flattens the elements in the same partition into an array. So you actually, when the RDD is small enough, you can glom and then collect to see how many there are in each partition. So in this case, first one had 1 and the second one had 2 and 3. So this is just a utry, so it's not an assignment, so you can try it yourself. And because here we didn't specify the number of partitions, and let's see what happens. Okay. It does some default of 8, right? And so if we change the number of partitions up here, it's going to be we specified 2 explicitly. You could have specified whatever, 800, 1800. So there will be lots of empty partitions. Okay. And why is this kind of important? I'm kind of dropping you in the deep end because you really need to know what's in each partition, and because parallel processing of lots of empty elements in the partition is waste of time. Okay, and this will bite you very quickly. when you're doing transformations of some RDD, and then these transformations are filters, they're reducing things in size, and so the original number of partitions will sort of flow through in your thing. So you have to really be careful about. Okay, so now if you lom and collect this guy, you're getting a lot of empty arrays. So take is nice actions. I'm asking it to only take 2 elements, so I put 2 there. That's bringing me 1 and 2. And you can take something else. You try taking 1, and that just takes 1. I don't know. What if you put 10? More than 10 elements, and then just does the minimum of the size and what you want to take. Okay. So you transform the RDD to a map to make another RDD. So this is the picture you want to have in your mind. And oh, right, we should break, right? There's coffee and from Commune, you might as well, right? Yeah, and I saw a couple people dozing off, so it's time for coffee. We should stop. There's no point in me just going on and on. But yeah, we'll just continue from here after a little break.